High-performance computing clusters are at the core of scientific research, simulation, and large-scale data processing. Coordinating compute, storage, and networking for these workloads is complex, and even minor misconfiguration can lead to downtime or inefficient resource usage. Deploying and managing Slurm manually on such clusters require careful attention to resources, all while maintaining high availability and optimal performance. These challenges can quickly become overwhelming, especially as workloads scale. Hello everyone, I'm Sanskriti Harmok, a developer relations at Vultr, and in today's Tech Talk, we will explore automating Slurm cluster deployment on Vultr Kubernetes Engine with the Slurm Operator. We'll see how the operator simplifies provisioning, scaling, and self-healing while VKE provides resilient, globally distributed infrastructure. By the end, you'll understand how this combination streamlines HPC workload management and ensures cluster run reliably at scale. So, without any further ado, let's get started. Before we dive into the deployment, it's important to understand what Slurm brings to the table. Slurm is an open source engine that drives large scale compute clusters, orchestrating jobs efficiently and ensuring resources are used optimally. But it doesn't just schedule tasks. It intelligently balances workloads across CPU, GPU, and MPI environments, making it suitable for the most demanding HPC applications. Most of the top supercomputers rely on it, which speaks to its scalability, flexibility, and robustness for extreme computational demands. Deploying Slurm isn't as simple as spinning up a single node. Its architecture involves multiple interconnected components, including controller, compute nodes, and databases that all need precise coordination. Storage is critical not just for the job state but also for accounting and logging, and misconfigured volumes can bring the cluster to a halt. Networking must be carefully tuned to ensure MPI workloads communicate efficiently at scale, because even a small misconfigurations impacts job performance. Without proper planning, maintaining high availability and fault tolerance becomes difficult, making manual deployments error-prone, slow, and challenging to scale for real HPC workloads. This is where the Slurm operator comes in, running natively on Vultr Kubernetes Engine. It transforms Slurm deployment from a manual error-prone process to a fully automated declarative workflow. With the operator, you define the desired state of your cluster, and Kubernetes ensure that the cluster matches that state continuously. You can increase or decrease compute resources with simple configuration changes, and the operator handles the orchestration behind the scenes. Upgrades and patching are also streamlined, reducing downtime and minimizing human intervention. The operator continuously monitors the health of every component, detecting failure and performing automatic recovery to maintain high availability. And when combined with VK's globally distributed compute optimized infrastructure, the operator provides a resilient platform that supports HPC workloads at scale. Now that we have covered the challenges and how the Slurm operator on Vultr Kubernetes Engine addresses them, let's see it in action. We'll walk through deploying a production-ready Slurm cluster, configuring persistent storage with Vultr block storage, and validating that the controller, compute nodes, and database are all running as expected. To see the Slurm operator at work, we first need a Vultr Kubernetes Engine cluster as our playground. Let's provision that environment and get everything ready for the deployment. For that, open the Vultr customer portal and navigate to Kubernetes under Products, and here click on Add Cluster to begin provisioning a new VK cluster. Start by providing a name to your cluster. Next, select the preferred Kubernetes version. Here, we'll go ahead with the latest one. Optionally, enable high availability for the control plane. This configures multiple control plane nodes behind a load balancer, ensuring redundancy and improved fault tolerance. You can also enable firewall. This will automatically create a new firewall group in which you can add rules later by visiting the firewall section present under network. Next, let's configure the node pool. We'll go ahead with the optimized cloud compute with 2 virtual CPUs, 4 GB of RAM, and 75 GB SSD storage for each node. Let's assign a label and set the number of nodes to this cluster. You can scale this number depending on your workloads. We'll stick with 3 for now. Finally, Choose a region. We'll go ahead with New Jersey and select an existing VPC network if available in the same region. Once everything looks good, go ahead and click on Deploy Now. This action will provision a fresh VKE cluster on your account. Now that our VKE cluster is provisioned and running, let's open its management page by clicking on it. Here, locate the download configuration button and use it to download the Kubernetes configuration file. This file contains credentials and cluster endpoint information required to interact with the cluster. Once downloaded, let's switch to our workstation to execute management and deployment commands. Before proceeding, ensure that both kubecontrol and Helm are installed and available in your system path. Once verified, locate the downloaded kubeconfig. Next, configure the local environment to use the downloaded kubeconfig file. Finally, verify the connectivity to the cluster by listing all nodes. With our VKE cluster up and running, next step is to check the available storage options. Kubernetes exposes these through storage classes, which define how persistent volumes are provisioned and managed. Let's list all these storage classes in our cluster to understand what is available. From the list of storage classes, our focus will be on the default one, which is Vultr block storage, as this is what we'll use for provisioning persistent volumes for Slurm cluster components. Before deploying any components, we first need to configure Helm repositories that host the charts for the tools our cluster will rely on. This includes Prometheus for monitoring, Metric Server to collect real-time cluster metrics, Bitnami for a stable and production-ready charts, and JetStack for Cert Manager to handle automated TLS certificate management. Once added, let's update the local Helm cache so that all charts are available for installation. Next, we'll install Cert Manager. This component automates TLS certificate management for Kubernetes, which is critical for secure communication between cluster components. We'll install it in its own namespace and ensure all CRDs are created. Now, let's deploy Prometheus, which provides monitoring for the cluster and Slurm workloads. By default, the stack includes Prometheus, Alert Manager, and a set of alerting rules giving us the visibility into cluster's health and performance. Now, as you can see, along with Prometheus and Alert Manager, the stack also installs Grafana. This gives us a powerful visualization layer on top of the raw metrics being collected. Before we move on to downloading the configuration files for Slurm, let's quickly check Helm releases currently installed in our cluster. This gives us a clear snapshot of what's already running. The output shows us that Cert Manager is installed in the Cert Manager namespace and Prometheus is running in Prometheus namespace. Both releases are in the deployed state, which means our prerequisites are in place. Now let's download the default configuration file for the Slurm operator. This file contains the base settings required to install and manage the operator itself. We can use it as a template and tweak any parameters before deploying. Next, we'll grab the default configuration file for the Slurm cluster. This defines how the actual Slurm workload manager will run inside our Kubernetes environment, including node roles, resources, and scheduling behavior. Again, we'll have the flexibility to adjust this file as needed before deploying. Now that we have downloaded the configuration files for both the Slurm operator and the Slurm cluster, let's quickly list the directory contents to confirm they are here. With the configuration file in place, let's go ahead and install Slurm operator using Helm. We'll specify the chart from Slinky project's container registry, pass in our custom values operator.yaml, set the version to 0.3.0, and deploy everything in a new namespace called Slinky. Once the installation command completes, we can verify the deployment by listing the pods in the Slinky namespace. Here you should see the Slurm operator pods in a running state. That tells us the operator is ready to manage Slurm clusters in our Kubernetes environment. Everything we have done so far was about preparing the environment, from setting up Kubernetes, installing dependencies, to deploying operator. But now comes the most important part, which is actually deploying the Slurm cluster itself. In the installation command for the same, we pass in our value slurm.yaml file and explicitly set a storage class to Vultr block storage. Notice that we are applying the storage setting not only at the global level, but also for critical components like MariaDB database and the Slurm controller. We are installing the version 0.3.0 into a new namespace called Slurm. Once we run this command, Kubernetes will will create all the resources required for a fully functional Slurm cluster. Once the chart is installed, let's verify the deployment by watching the pods in the Slurm namespace. In a few seconds, you should see components like the MariaDB database, the Slurm controller, and the compute nodes, all managed by the operator, transitioned into a running state. Now that the Slurm cluster is up, let's connect to the Slurm controller pod. From there, we can run a standard Slurm commands to confirm that the cluster is working as expected. Let's first open an interactive shell inside the controller pod. Inside the controller, run sinfo to check the status of the compute nodes and partitions. Finally, use srun to launch a simple test job across 5 nodes. This will output the hostname of the nodes allocated to the job, confirming that scheduling is working. With these steps, you now have a fully functional Slurm cluster running on Vultr Kubernetes Engine managed by the Slurm Operator. You can extend this setup by customizing workloads, integrating additional monitoring, or scaling node pools as needed. All the commands I used in this demo are documented in a supporting reference guide, which is linked in the description below for you to follow step by step at your own pace. To summarize, deploying Slurm on Vultr Kubernetes Engine with the Slurm operator simplifies cluster management, ensures high availability, and allows efficient scaling for HPC workloads. If you would like to experience this yourself, then get started on Vultr today with $250 in free credits on a new account using the promo link attached in the description below. If you have any questions or want to connect with other users running Slurm on VK, then join the conversations on the Vultr community forum. Thank you so much for tuning in. We hope this tech talk helped you streamline HPC workload management.